This is our 8th brown bag lunch presentation. Thank you, Paul, for putting all of these together. I know it's been a lot of work. This one is titled Monitoring Urban Waterways, DPR Surface Water Protection Program. As you heard, I'm Brian Leahy, the Director of the Department of Pesticide Regulation. I want to thank you all for coming today. I want to welcome our folks tuned in on the webcasting. We're going to try to get this thing done at 12:55, so that means we're going to start taking questions at 12:45, so be brief. And if we start to hear a funny sound or a noise or you smell something funky, we're going to go out those doors, go down the stairs, go across the street to the Cesar Chavez Park, and everything will be great. The Surface Water Protection Program protects health and the environment by preventing pesticides from adversely affecting our surface waters. We do that by examining agricultural and non-agricultural or urban sources of pesticides, pesticide residue in surface waters. Our program has preventative and responsive components that reduce the presence of pesticides in surface water. Today, we have 3 of our scientists. We're going to start with Yuzhou Luo. Okay, he was going to create. Then Robert Budd and Michael Ensminger, who will provide an update on recent findings in urban waterways. So, Yuzhou, will you start the program? Thank you very much.
DPR's surface water program protects human health and the environmental based on the emission of the surface water quality protection. In our program, surface water is evaluated based on the pesticide effects on the aquatic sensitive species. Multiple components are included in our program, including pesticide prevention, monitoring, mitigation, modeling, assessment, outreach, and regulation. Mathematical modeling is a very important part and actually incorporated in most of those components. Today, I will mainly focus on the pesticide prioritization model for surface water monitoring, but also give a brief introduction on the sister model for pesticide registration evaluation. Actually, those 2 models are related closely. Here shows a general procedure. Pesticides have to be evaluated before being used in California. The registration evaluation model is developed for this purpose in terms of surface water evaluation. And only a very small portion of the pesticides used in California will be monitored by DPR, and the prioritization model will be used for the monitoring project planning. Generally, DPR will evaluate pesticides to be used in California. Surface water evaluation is just one of the evaluation processes. Historically, our evaluation was mainly based on professional judgment. But since 2012, we have been developing a more consistent, transparent, and efficient modeling approach to standardize the evaluation process. The modeling results are also called registration recommendations, including not to support registration, to support, or to conditionally support. Pesticides with conditional registration are also considered as potential candidates for surface water monitoring. And so we prepare the analytical methods and also watch the pesticide use amount and use trend in California. For the pesticide monitoring in surface water, the most important questions are where, when, and what to sample. There are hundreds of monitoring sites in California, historically and actively operated by DPR and other agencies. Behind each of those monitoring sites, those questions have to be asked and answered in the study plan. Specific to DPR, here shows a real example for the sampling schedule for this year's agriculture pesticide monitoring. As mentioned before, it's required to clearly document the sampling locations, the sampling seasons, and the chemicals to be analyzed. Obviously, we cannot sample everywhere, anytime, and for everything, so we have to optimize our selections based on the relative importance of the pesticide risk and exposure. That's why the project planning and scheduling is also called prioritization. The modeling efforts was started in 2012 when the prioritization work group was developed in DPR. The output of this project is a computer model which generates a priority list of pesticides within the user-defined domain of time, space, and many other conditions. The modeling results will be incorporated in our monitoring program. For example, the sampling schedule I showed before was actually based on the model. Here shows the web page for the project, including everything, the technical reports, user's manual, and the model instruction. You can also download the model for your own application. This is our first model released by Surface Water Protection Program for public uses, because we think the monitoring prioritization is a very general topic, not only for DPR. And since 2013, some of the modeling components or the model itself have been used by state and federal agencies in their own study. The model is started with the pesticide application. Here I'm talking about the outdoor pesticide uses, usually applied on soil and canopy, but sometimes on paved surface, building surface, or directly application to water. Pesticide application is not a problem by itself. The problem is the offset movement from the treated area to surface water. The driving force is mainly the surface water runoff induced by rainfall and irrigation. Within the surface water is the pesticide transport processes by following the stream network and the watershed delineation. The transport could be long-term or short-term according to the location of the monitoring site. And each of the monitoring sites, the pesticide levels are quantified by chemical analysis and toxicity tests in order to describe the pesticide effects on aquatic sensitive species. Input data are required for each of those modeling components. The very important one is the pesticide use data. We also require environmental description, chemical property, and toxicity data. Pesticide use data are based on DPR's pesticide use reporting or PUR database. Agricultural uses are associated with very high resolution and reported as daily data for each section of 1 square mile. Here shows an example for the chlorpyrifos used in California. I just zoom in and focus on Sacramento surrounding regions so you can see the sections with different range of pesticide uses. This map already gives us some very useful information on the pesticide distribution and spatial variability. Urban data of PUR are reported as monthly data for each county. To have a consistent resolution, we converted the PUR data to monthly data and the scale of watershed. Watershed delineation is based on the USGS National Hydrograph Database, or NHD. We are using the highest resolution. It's called a 12-digit hydrological unit code, or HAG12. For your information, there are 4,500 watersheds in California. Other data include the pesticide chemical analysis property database from IUPAC and the aquatic life benchmark by US EPA. As mentioned before, the first step in the modeling process is the spatial data analysis to convert the pesticide use data or PUR data to watershed scale. Pesticide transferability into surface water is classified by pesticide use pattern, application method, and the chemical property. Once getting into the water, two major processes are considered in the model, including the pesticide accumulation by water conductivity and the pesticide degradation according to the travel time within each watershed. And the sampling location, adjusted pesticide use amount and associated toxicity to sensitive species are combined for the monitoring priority. Two sets of variables are used in the model. Priority scores are developed for pesticide use and toxicity. For example, the use scores range from 1 to 5. The higher the value, the more the pesticide used. and its toxicity scores from 1 for lower toxicity to 8 for higher toxicity. In addition, a bunch of indicators are developed for pesticide fit and transport, including a pesticide use pattern, application methods, volatility, runoff potential, aquatic persistence, bioaccumulation, and bioavailability. And this is the model user interface. The model will ask some general questions such as the pesticide use pattern. You can select agricultural use, urban use, or just specify your own use pattern. You are asked to select the toxicity data sources. We usually use the US EPA aquatic life benchmark, but we also have the options for drinking water standards and human health benchmarks for more general use of the model. In the panel for the advanced options, you have the chance to refine your study domain by selecting the months, counties, and many other conditions. For the watershed delineation, we have the options for USGS-defined watershed, user-defined watershed, and even for the statewide prioritization. We call this a spatially continuous mapping. The first example is a model application to site-specific prioritization. That means we already have a predefined monitoring site, but just want to identify the top pesticides for monitoring. The site for demonstration is located in Alameda County for urban receiving water sampling, as shown on the map. In this case study, we are using the 3G urban PUR data and based on the acute aquatic benchmarks for the risk assessment. This is a screenshot of the modeling results showing the top 10 pesticides for the suggested for the monitoring. The first two columns after the chemical name are pesticide use data within the watershed and associated use score, followed by the benchmark values and associated toxicity score. And finally, the final score is just the product of the individual scores, which is designed to arrange the priority list from higher scores to lower scores. We also compared our results to what we have sampled at this location and found a good match. So this supports the model comparability and the model future use for the monitoring project design. The next example is a model application for the statewide prioritization. We choose the urban use of Bifenthrin as a test agent and plot the modeling results on the map. The darker color indicates higher priority for monitoring. So those are mainly located in Sacramento, Bay Area, Orange County, and San Diego. Also on the map is our DPR monitoring network for urban pesticide uses, including Bifenthrin. As you can see, we generally covered the hotspots identified by the model. And my colleagues will give more information on our urban monitoring program.
Well, thanks, Yuzhou. Good stuff. I'm going to change gears a little bit here and talk a little bit more on the practical side. I'm going to use some of the information that Yuzhou presented, and I'm going to talk about how we incorporate that into our modeling. And then I'm going to talk about the who, what, whens, and wheres. Well, not the who's. Hopefully you already know the who's, right? But the how, what, and wheres of how we do our urban monitoring. And at the end of this talk, you should be able to answer all these questions. I won't give you a quiz, but first of all, I want to talk why in the heck should we monitor in the urban environment anyway? You've probably asked yourself this question a million times, right? Why in the heck do we monitor in the urban environment? When I think about pesticides, especially when I worked in the ag industry, I thought about pesticides applied to agriculture. Maybe you're concerned about worker health and safety and being exposed when things are applied, and so you would think about agriculture. Or maybe you're interested in residues potentially on your food, and you would think about agriculture, and you may not have given much thought about urban use. And I just want to get across the point in this next slide or two that there is a high urban component in our environment that you may have not have considered if you had thought about pesticides. I just have a little pie chart up here. Well, a lot darker here than on my slide, but this is from the 2013 PUR pesticide use database summary of all the data. And you can see agricultural applications from the PUR is about 178 million pounds. That's a lot of agricultural applications, right? And then if you look, the purple and the yellow, those are smaller. The yellow is actually urban applications by structural pest controls and landscape management. It doesn't look like a lot. But notice I mentioned that these are all that I've talked about so far are what we have in our use data. We have a lot of use data that's not recorded in California, and it's what's applied by homeowners. And I just put a little red chunk there. It's been estimated that homeowners apply anywhere from 20 to 70% of all pesticides being used in the environment. So I just did a little conservative estimate of 25% of probably of what's used in the homeowner. Now, still that doesn't look a lot compared to ag, but if you delve down into the ag use a little bit more, you'll see things like fumigants, a big chunk of sulfur, a big chunk for like petroleum and mineral oils that you maybe not think as your traditional pesticides. If you take those out, you notice that ag use and urban use are about the same. Like I said, this is a very conservative estimate of urban use. So, bottom line, we have high use. Why else is urban monitoring, urban runoff a concern? Well, one, lot size is one. When I grew up, I had my parents owned one house on an acre of land. Here in some of my sites in Folsom and Roseville, we have 6 homes on 1 acre, and that's not atypical. So a lot of people are applying pesticides around their home. And also a term that I like this term, I just heard it recently, continuous connectivity. If you look at your house or this house in these photos, and these are from my sampling sites in Folsom, there's concrete almost all around those houses, right? So and we know that when it rains, water doesn't go through that concrete, right? It's gonna go off. All these homes are sloped to the street. They're actually sloped downward. If you look around your house, it's generally sloped to the back and to the sides. So all this stuff will actually come off into the street. To get that off so we don't have to worry about flooding. And then finally, if you're an engineer and you look under your feet when you're out in your neighborhood, there's this whole network of storm drain systems, right? These cities are designed to get the water off fast, take it out to the storm drain system. This system's not cleaned in your wastewater treatment plant, and it just goes to your nearest urban creek and river. This picture I borrowed here. Left-hand side is more of the typical, lots of grass, lots of pervious surfaces for water to filter down. On the right-hand side is a picture of a city. A lot of impervious surfaces, water can't penetrate, so it just runs off into the storm drain system. This one says impervious surfaces about 75 to 100%. We know in some of our monitoring areas we're about 55 to 65% impervious system. So a lot of stuff just coming off when it rains, when you wash your car, when you hose down your sidewalk, getting into the urban storm drain system and going out to the creeks. Why else is it bad? Well, we don't like spiders and we don't like ants, right? Nobody likes spiders and ants. We want to get rid of them. So we designed pesticides to kill these things, and these things get applied, and they're highly effective. They target their organisms. They do an excellent job. Unfortunately, when this stuff goes into the water, it does a really good job of killing aquatic insects too. And some things that we're interested in that get into these creeks and rivers are a real concern because they're just as toxic as they would be if you sprayed your ant or your spiders. The next 2 questions on my list, what to monitor and where to monitor, I'm just going to answer in the same slide. This was actually just covered by Yuzhou, so I'm going to give you a user's end perspective of our prioritization program. Prior to 2012, when I started working on this project several years back, it was left up to your best professional judgment. DPR hired an environmental scientist. The environmental scientist has training, has schooling, has experience. Look at some data and design what to monitor for. Since 2012, we have this really cool program that actually inputs tox data, inputs use data, and spits out a priority of compounds that I should monitor for based on the area. I can do it statewide, I can do it countywide, I can do it many, many countywides. So actually, I just printed off a sheet from our most current a monitoring year. And there's things on there that if you're familiar with pesticides, you might be familiar with. A lot of pyrethroids, right? Permethrin, Bifenthrin, Lambda. There's also things on there like a lot of fipronil and a lot of herbicides, things that if you were like an old timer like me, you'd say, yeah, those are pesticides that are a concern. But what I like about this program, now it actually starts to select things that I wouldn't normally think about monitoring for, and that's highlighted in yellow. Things like the herbicide sulfonylurea or the insecticide chlorphenapir that now we should be thinking about, should I monitor for those? And actually, because of this program, we just added chlorphenapir to our program. We had the chemists come up with a new procedure to do the analysis, and probably we'll do the same thing for sulfonylurea in the future. Another map that Yuzhou showed is another part of this program where I can look at the watersheds that have the highest use. And on the display in front of you, I just show a picture of Bifenthrin because that's one of our more pesticides we're concerned about. I can run the model and get a printout of where probably are the higher usage areas of Bifenthrin. And lo and behold, it's in the higher urban areas, right, for what I'm looking for. But we can do this for fipronil, we can do this for any analyte. We can see where we probably should be monitoring. So, bottom line, where do we monitor? We monitor in Northern California and in Southern California. The project is divided into two regions. I do all the Northern California work. Rob does all the Southern California work. In Northern California, we're interested in the high use areas. Things like in Folsom. We've got several sites in Folsom. We have several sites in Roseville. We have a new site in Sacramento at Arcade Creek. We know that these sites tend to have a lot of runoff, and they had to have a lot of pesticides in that runoff. In the San Francisco Bay Area, I also monitor in the East Bay. You'll notice there's nothing much in the, I don't know what they call the West Bay or the North Bay. Marin County in San Francisco, they don't use a lot of pesticides, but Alameda County, Contra Costa County, Santa Clara County, there's a lot of pesticide use there. So we're going to monitor in those spots to see what we can find. Southern California, we also have many other spots down there. Orange County has been a very lucrative spot for our sampling because we find a lot of detections. We've got several sites in Orange County. We have several new sites in LA County that also tend to be fairly contaminated. We know LA County has some of the highest use of our AIs, so it makes sense to monitor there. And also we've got a site or two in San Diego. I've mentioned storm drains and, oops, looks like I need to advance that one. Storm drains and receiving waters. I'll talk about that in a second. Generally, we tend to monitor at both of these types of sites. In the where to monitor, storm drain outfalls are like the picture on the right-hand side. This is one of my sites in Roseville. We monitor our storm drain outfalls because we can actually get the storm drain maps from the city. We can then go ahead and outline where that runoff is coming from based on the storm drain maps and the slope. And so we can outline these areas. You see yellow, green, and red. And we know what houses are actually contributing to that storm drain outfall. We also monitor receiving waters, which is the downstream site. Sorry, I had to throw my little cartoon up there. So in the storm drain outfalls, we can actually do the individual neighborhoods, right? And so this has been very helpful when we look at trends and things like that. Receiving waters gives us a more of a whole watershed, or at least a whole city look at what's going on. So here in Roseville, I've got a site further downstream. It collects most of the water from Roseville. So I can kind of know what that whole Pleasant Grove Creek watershed is doing, especially over years. We've been able to monitor now for 6, 7, 8 years in this project. When to monitor? Well, you know, California has a dry season, right? And they have a wet season, or at least they're supposed to have a wet season. And California is pretty nice because we can divide those two groups up. We can monitor a couple times in the dry, pretty much know between May and September it's not going to rain, so we can plan trips around that. And then we know pretty much from October to May or so it's supposed to rain, so we try to monitor both of these two types. In the rain events, we try to do the very first rain of the year because that's when we get our most flush. We get things that have been applied all summer long, right? Nobody's hosed down, especially this year because you're not supposed to hose your sidewalk down and things like that. First flush, that should be really high in concentration. So I know a couple things. We know in the dry season, actually, we actually get, if we look at the whole dry season, we've done some work showing that probably just total amount of pesticide coming off when it's dry is probably higher than it is in rain events. And that may at first not seem intuitive, but when you figure we only have, what, maybe 8 or 9 storms a year, and the rest of the year it's dry. So we get a lot of stuff just coming out from people washing their cars, irrigation, drool, hosing down things that just happen during the dry event. We also then like storm events because they tend to give us higher concentrations for that period of time, and we get a much higher detection frequency of things we're looking for. So we tend to monitor both about twice a year. So I just have a couple slides of how do we do it real quick. A lot of pictures here, but we'll go out to the field and we'll collect these samples, and we either do it by bottle. We've got some models here. Just take a bottle. If it's very shallow, just dip down and grab the water. We may do it on the right-hand picture. That was pretty shallow. We couldn't get a bottle down there, so we'd use a little secondary container and dip into the container and then put it into the bottles, and we'll collect. If we're looking at 10 different pesticides at a site, we'll collect 10 different bottles, and that's not uncommon. Send them to the lab. The receiving water, especially one of my scientific aids in the lower picture, if the stream's wide, we can't get out there, we can actually take a pole and we can dip in and collect those samples. We've been more recently going to some of our sites to automatic samplers. This has been very, very nice. These are generally set up with some contracts with UC Davis, and it allows us to collect samples over time. This has been in auto sampler. You can see the picture. It says auto sampler, so that's the auto sampler. These are in these big greenly boxes. We can put other equipment in there like flow meters. So wherever we have these set up, we can measure flow. We can take samples, and then they're locked away to keep people and kids with inquisitive minds out. And there's just a couple examples. The right-hand picture is from my Folsom site. The left-hand picture is from Orange County sites. These have been very valuable for up here. We've actually been able to set up a contract and have the UC Davis folks collect samples over the entire storm. And we can collect, we're looking at some mitigation stuff Rob's going to talk about, but we can look at total inputs into an area during a storm event. So total mass, that's we've never been able to do that before. Southern California, Rob wakes up at 2 a.m. and it's raining down there. He can't get down there like I can up in Roseville or Folsom. So he's through another contract, he's got a person at UC Davis that actually will set these auto samplers up, and they can actually kind of collect as he's driving down there. Not all his sites, but some of his sites. So it can be a really time saver too, and prevent us from missing some storms. I haven't talked about it, but we also are interested in sediments. Some things that we look at, some insecticides that we look at, really bind really strongly to sediments like pyrethroids. And so if we can collect sediments, that'll give us another perspective of what's happening in that area. We just kind of do this either with a little trowel or shovel. We kind of scoop off the top layer of sediment. You can see both the top pictures where we're collecting sediment and we're putting it into a little container. You can do it as the bottom left picture. You can do it actually by siphoning it up. And more recently, we've actually gone to putting traps, what we call sediment traps. These are just stainless steel containers. We can put them below the water level. As sediments come over, they collect the sediments, especially if we can get a spot where the water kind of stops flowing and stands still for a little bit. And the best thing about these is we can actually take them out in 6 months, and we know we have fresh new sediments. We can put a new one in that doesn't have any sediments, and we can collect sediments in another 4 or 5 months, and we can see what's happening to that watershed or that area over a period of time. We also do water quality measurements. I just got some pictures of some meters here in a site in Southern California where one of the scientific aides is walking into the water and going to drop a meter. We measure things like water pH, turbidity, dissolved oxygen, just important parameters to state overall what the health of the stream is. And so I'd like to show this little video if I can. I might need some help on that. Sorry, Paul, I should have warned you ahead of time, but this way I'm making sure you're awake. This is about a 2-minute.
Go ahead. Is it part of the PowerPoint?
It's in the PowerPoint, yeah. I don't have I need a mouse, and it was doing something funny where it first didn't come up. Here we go. Give you a little example of what we do and how we do it.
PGC 025. And the 15th, of course, we'll do sample side time at 10:45. This thunder, I told you I heard thunder.
Yeah.
10:45, rainy, storm event. Temperature 13.2, 0.08. Salinity 0.06. pH 6.97.
Really? Go. I got it.
Okay.
Right.
Excellent. Let's go home.
Absolutely.
Man.
So that's kind of what we do. You can see how scientific we were in the taking the data there and stuff. Keen took that video, so thank you, Keen, for that. Sometimes we drag him out and make him go out in the rain with us. We were pretty lucky in this particular day. Right when we were done, it started to hail pretty hard. And we were driving back. It almost looked like there was snow accumulated on the side of the road. There was so much hail. Just a little example of what we do. This is a rain event, and we do the same thing during dry seasons, and you can notice some of the sites we might have to walk a little bit too. Nothing too dangerous. So, what happened? All right. Well, that slide either got changed or the next slide with the 2-slide section should be 1 slide at a time. The next one, click on the next one. Oh yeah, it wasn't on slideshow. Sorry, I put it on slideshow. Got bumped out. Thank you. Thank you, Paul. So, I won't show the video again. So you might think, what the heck do we do with all the data? We've been collecting data since 2008, 2009. And so I just put a slide up here of all the data that we've collected and detection frequency, one thing we look at. From all our sites, Folsom, Roseville, Orange County, just all lumped together to kind of get you an idea of what we're looking for. Detection frequency is on the y-axis, and then just the chemicals on the right-hand side. And you see a lot of detections up there, right? There's 17 compounds up there that have been detected at greater than 10%, some of them pretty high. We also know there's about 10 other ones that we've detected less than 10%, not as frequent. And you might look at that and say, wow, that's bad, right? There's a lot of detections, a lot of stuff out there. I'm sure that's bad. Well, is that bad? Well, it may or may not be bad. A little sneak preview, I gave you this slide. So I went ahead and whenever we get detections, we kind of compare them to aquatic thresholds. And one of the thresholds we use is the US EPA Aquatic Life Benchmarks, which Yuzhou mentioned briefly in his talk. And so this slide, I changed it a little bit, and I put in red everything that's detected at concentrations that are above these aquatic thresholds. These are things that are going to be toxic to aquatic organisms, and we might be concerned about those. Things in green, yeah, there are a lot of detections, but they're not detected at very toxic, potentially toxic levels, and so we're not probably quite as concerned about the things in green, although just because something occurs all the time may also be a concern. But the things in red, and what pops out in your mind are things like pyrethroids, boom, very toxic, frequently detected, bifenthrin, permethrin, psifluthrin. These things, especially the bifenthrin, detected quite a bit. Other things you might notice on that slide is fipronil. We detect a lot of fipronil, especially in Southern California. Fipronil is very toxic to aquatic life. And the other thing that pops out that may be toxic is the last remaining OP, organic phosphate insecticide, malathion. When we detect it, it's usually detected at levels that are toxic. So when we look at the data, then we start looking at things that may cause concerns and try to address those. Maybe mitigation or label changes, things like that. We also, because we've been blessed with having so much data, we can start looking at trends over time. This has been very helpful with the pyrethroid regulations that were installed in 2012 to try to curtail the runoff of pyrethroids. We can now look at our data and do a trend analysis over time to see which way are bifenthrins going. Are they going lower because that's what we would expect with the regulations? Are they staying the same? Are they getting higher because people are being used? So I just have a little slide here, just kind of an example. This is actually from my Roseville sampling sites. And you can plot the data, and you can see a little bit of a downward trend on that. Unfortunately, we don't have any significant trends yet. If we do run the stats on that, we don't have any statistics that say that we are seeing decreases. So we probably need to run this over longer periods of time, more and more years yet. And my last slide, my last point, all our data is publicly available. Every year our data goes in the surface water database. It gets updated every spring with all our new data. We always write reports in the right-hand side. We'll write reports, and usually by the end of every calendar year, the reports are written from the previous fiscal year. You can get our data off of there. You can always contact us. And sometimes we have the luxury of writing journal articles, which Rob just wrote a really good one on fipronil use. So with that, Rob's going to talk a bit.
Thanks, Mike. Mike covered all of our ambient monitoring program. So I'm just going to take a really brief few minutes to describe some additional information that we've been collecting since the inception of our program. So one of the first questions that comes up during these conversations is, yes, you've been detecting pesticides, but who cares? Well, if you're this ugly space alien looking creature right here, you do. This is the Hyalella azteca, which is one of our test organisms for water quality. And we have a contract with the UC Davis Aquatic Health Program to do toxicity tests at a subset of our locations. They do a 96-hour exposure with Hyalella and then just do a % survival count. This is a summary of all the toxicity tests that, for all of our sites in Northern and Southern California. The higher the bars in these graphs, the less toxic the samples are. The red bars indicate the samples collected during the dry season, while those in yellow indicate samples collected during storm events. So obviously, the stormwater is much more toxic to the Hyalella populations, and this indicates a higher concentration of pyrethroids and also highlights the importance of stormwater for transporting pesticides off the urban landscapes. So now that we've identified problems of pesticides in our surface waters, we're also interested in methods for reducing or mitigating those concentrations. So besides regulatory action, there's several physical mitigation strategies that can be employed to help reduce concentrations. These include constructed wetlands, vegetated ditches, and various filters. Because of the nature of the landscape, small constructed wetlands are the ideal choice in urban landscapes. So here's a couple of animation slides. Once a pesticide gets into surface waters, they have the ability to either be transported downstream or sorbed to vegetation or sediment. So in an effective mitigation system, it wants to maximize the sorption sites to help bind the pesticide and prevent that downstream transportation. All mitigation systems want to help slow the flow to allow more time for natural chemical transformations to occur, such as photolysis and hydrolysis. And then wetlands in particular are an ideal habitat for providing microbial communities that can use the pesticides as a food source, therefore leading to their degradation. We've been monitoring 2 wetlands in our monitoring scheme to help evaluate their efficacy in reducing pesticide concentrations. And this is simply done by comparing the concentrations measured at the outlets versus the inlets of the systems. This slide represents the % reduction of Bifenthrin in both of our wetlands. And Bifenthrin, as Mike mentioned, is one of our highest detected pesticides in our ambient monitoring. So at the higher the bar, again, in this graph represents a larger % removal in the system. The yellow bars represent the samples collected during the dry season, and the storms are represented in red. It's obvious that there's a higher percent removal during the dry season. However, I'm optimistic in that there's greater than 20% removal during our storms, which is when we see much, much higher flow regimes. So this is good to me, good news.